Hi everyone, in this video I will explain the definitions in the STKO for OpenSees, and in the last video I discussed about the Coulomb friction definition. Now I have this velocity dependent multilinear definition, so I will rename it with velocity dependent multilinear function. And then as I already have selected this, and I have these two requirements for the velocity point and for the friction point. So velocity is an independent variable here, while friction points are independent, while friction points are dependent, while velocity points are independent. And in the context of civil engineering, particularly in the field of fluid dynamics, there are various multilinear velocity-dependent functions that play a very important role in modeling and analyzing the behavior of fluids. And I think one such example is Navier-Stokes equation, which are fundamental in describing the motions of fluids and the force that are acting upon them. So when you are working with OpenSeas, by utilizing its capabilities for the finite element analysis of extreme events, then the Navier-Stokes equation can be used to model the behavior of the fluid in various practical applications. And uh, one such practical application is in the OpenSeas is fluid structure interaction problem. So, for instance, if you are simulating and analyzing a dam or a bridge that is subjected to flood or tsunami loading, then the Navier-Stokes equation can be used to model the behavior of the water and its interaction with the structure. So the equation can be discretized using the finite element method that we chose here, and then we solve them numerically to obtain the velocity and pressure fields in the fluid, which can then be used to compute the force acting on the structure. So FSI structure interaction is an important um, aspect to consider, and we should be very careful about it. So for example, I have a function here. I need to define same number of rows for the velocity points and for the um, friction points for these two here. So let's say we have 5 for the velocity points. The first one is 0.1, then it is 0.3, it is 0.5, then it is 0.4, and then 0.01. Something like this. The reason is that at some point the friction increased, then it reduced drastically when the velocity increased. Since we are defining the velocity point, so for example, 5, 10, 15, 20, and then 30. And sorry, I consider this as a friction point. So 5 vectors have been included here, and in a similar manner, 5 vectors are required here. So for example, 0.1, 0.3, 0.35, then 0.1, 0.05, and then 0.001. And what's the reason is if the velocity increase, then the friction decrease in between them, and so on. So I defined this as a function here, and let's click on this as well so that I can discuss it, and click on OK. So it's not yet assigned to any domain, but From the convention, we can see here that we have this keyword of friction model, velocity dependent multilinear functionality here in the STKO. And if we go to the OpenSees command here, then it works like this. Make sure if you are working on this document here, for example, then by default using the OpenSees, if you are considering it in this way, that you want to use directly this function, then it's difficult for you to assign it. The reason is um, we have some sort of uh, difficulties by incorporating them in the OpenSeas command line directly. So we have to prepare the tickle file and then call it from the OpenSeas interpreter, and after calling it, then we get the same line of code that is given here. So let me explain it, that how it's working here. This one is the tag here. So if you look at here, we have this tag that is given here, and this is the name of the friction model. This is the context of the coding that we are using here. So this friction tag, it is a unique friction model object tag that is required here to consider, and this friction tag is basically this velocity and this friction, this name that we are using here. While for the velocity, we are getting this discussion here, right? And then for friction, we are getting this discussion here. So for friction tag, our velocity points, for example, this is 1. So it means that we are using 1 as a friction tag here, and this one is in the STKO, this tag that we are talking about, this one, it is closed in the brackets here. So in order to do this with the STKO, sorry, OpenSeas, you first need to, just in case if you are working with technical language, you should understand the basic set foot functions in your definition here. However, let's write this. So in order to write it for the OpenSeas, you need to like write this, then multilinear. This function is the function that you need to consider. Then this is the tag that the STKO is assigning here. While now there comes the role of these three definitions here. So after writing these three definitions, these two are constant. You should be very careful about this. Do not let any grammatical mistake ruin your model. Then this dollar sign basically shows this numerical value that is assigned to this friction model, multi-linear velocity dependent friction. And after this, we have these friction tags. We have this discussion on velocity. So you don't need to write anything else except you have to write it like this. So what I did here, I write for the velocity points 5, 10, 15, 20, and 30. So I should write it like this: 5.0, 15.0, 20.0, I think, and 30.0. After that, we have to consider the friction tag here for the friction points. So minus fin, then for the friction, we have point 1, point 3, point 35, 0.1, 0.3, 0.35, 0.05, and 0.01. So 0.001. So in this way, you write it in the STKO environment. But the thing is, if you are working with the OpenSeas directly in this way, then it won't work. So by pressing enter, OpenSeas will not understand the syntax here, uh, right? So we have to first define these in our model, but this is how you need to write it. You can see here, this is something like this. And if we try to link it, then there are some DLL errors that are arising in the model. So we can directly call the OpenSeas file, the tickle file in the OpenSeas, but first we have to prepare them. And I will show in the model of the frame that I'm going to analyze in the next few videos after completion of this basic introductory course, um, which will show you how you can use the OpenSeas here. Anyways, this model, as compared to the previous one, this is a detailed model with the particles that when the particle velocity is changing, the friction is changing. The previous one is not dependent on the velocity, and this one is completely dependent on the velocity here. So this is very important. And these multilinear velocity-dependent friction models that are implemented in OpenSeas elements, such as in the documentation, it will be given for the triple friction pendulum bearing elements, similarly flat slide bearing elements, single friction pendulum bearings. With respect to time, the velocities change here, and you can see here the flat slider bearing element. This is related to this. So we have these tags here for the definitions, and all these informations are included here. So you can download them, these tickle files, and then you can study them to see what's going on in the model, and you can simplify things for yourself. So I will be covering these topics up to the completion of this course, this introductory course. But currently, I want you to familiarize with the interface of the STKO and how it's working. So upon completion of all these parameters, I will then later on switch to all the details that are required here. In a similar manner, after this, I need to define the velocity dependent material. And for the velocity dependent materials, for the model definition, the friction, I will further discuss some aspects. And then at the end, I will relatively compare all these definitions in the friction. If what are the shortcomings that are occurring in these models here. So we have this friction model. Then I will switch to the limit curve rotation, and then miscellaneous custom definitions, and then all these definitions that are given here. Right. So everything that is given here will be covered in the explanatory videos. Then I will write the other details about the course that I'm going to continue. So thank you so much for watching.